No, I am recording.
Okay, so today we have a talk by Professor Kirilov, and his talk is titled Using Symmetries to Solve Problems, Introduction to Representation Theory.
Okay. Hi, guys. So let me see how many of you I know. Well, I think about half. Okay, so just in case, so yes, my name is Sasha Kirilov, and my field is representation theory. So I wanted to tell you a little bit about that, but rather than give a typical lecture with beginning with the definitions and proofs and all that, I thought that I would give you an example problem, or rather a couple of problems, beginning with a baby problem, which is really simple but also fun, and ending, if time permits, by something really interesting, namely by understanding the spectrum of the hydrogen atom in quantum mechanics. We'll see how far I will be able to get. By the way, my understanding is that the talk is supposed to be 1 hour, correct?
Yes.
Okay. So, and as usual with all the talks, I mean, that's not a formal thing. So if you want to ask something, you have some comments, you have some questions, feel free at any moment to stop me and ask your question. Probably better do it using voice, because I'm not sure I will be able to read the chat if while talking. So asking question using voice is probably easiest. Can you all hear and see me well?
Yes.
Okay. Okay, so let me start sharing the screen. Okay. So that's my favorite iPad. Okay, so let's begin. So what exactly is representation theory? Well, as I said, it's basically a proper language and proper set of tools for exploring various symmetries. And let me begin, as I promised, with a baby example. This example was actually invented by my father, who is also working in representation theory and is much better known than me in that area. But I liked it so much that I give it quite frequently in various classes I teach. So the example is as follows. Suppose you have a group of kids, say in a kindergarten, sitting around a round table. So you have a group of kids sitting around the table. Each has a bowl of cereal in front of him. And of course, the amount of cereal in each bowl is different. It so happened. So, and so on, all the way around the circle. And here is xn. Now, at some moment, as soon as the teacher leaves the room, the kids, of course, start misbehaving. What exactly they do? Well, what they do is the following. Each kid, say, let's look at, say, this one, kid number 2. So what he does is that he reaches into the bowls of his neighbors and steals some cereal from them. Namely, he takes half of cereal from the bowl of his neighbor to the right, and half of cereal of from the bowl of his neighbor to the left, and puts them in his own bowl. Of course, at the same time, his neighbors are doing the same to him. Okay. So the amounts of cereals, the distribution of cereal changes. Now suppose that the teacher comes and goes frequently enough, so this procedure repeats many times. So the question is, what happens after sufficiently many times? To be precise, we can ask the following question. Is it true that after sufficiently many times, distribution of serial will be about equal. It will be uniform. In other words, all amounts will be approximately equal. So that's a question. And that's, of course, a pretty straightforward linear algebra question, or so it seems. So what we have at every moment, of course, well, of course, that's not how you tell the problem in kindergarten, but all of us who have taken some linear algebra class understand how you're supposed to do that problem. So at every moment, the distribution, the amounts of serial can be described by some vector x in Rn. And of course, what this operation is some operation on Rn, namely it sends the vector x1 and so on to the following. So for example, what will be in place 2 here? Well, person 2 had stolen half of the serial. Let me make it larger. Second kid had stolen half of the serial from his neighbor to the left and half from his neighbor to the right. So, and they had together stolen all of his serial. So that's what he will have in position 2. So that's how much kid 2 will have after this operation. What about kid 1? Well, he has half of the serial of his neighbor on one side, which would be x2, and half on the other side, which would be xn. We are, after all, in a circle. So we'll have this. And so on. So that's our operation. As you can immediately see, that's a linear operation. So we denote this by A. So we have a linear operator from A from Rn to Rn. And our question is it true that basically the question is, can we say what happens if you do it sufficiently many times? That is to say, if you do take a large power of this operator, can we describe that? So that's the question, restated from serial translated into linear algebra. So that's, of course, we all know how you do such problems. Anyone remembers how you solve a question, what is the large power of some operator? Any suggestions? How we compute
maybe you want to diagonalize it?
Yep. So of course, so what you want to do is diagonalize that. And then, of course, computing a to the n is trivial. And in particular, if it so happens that a has one eigenvalue which is equal to 1, or at least equal to 1 in absolute value, and all others strictly less than that, then in the limit of power, so a to the n, where n goes to infinity, what will happen is that all the eigenvalues which are less than 1 in absolute value will become 0, and the one eigenvalue which is 1 will stay there, so you'll get a projector on the corresponding eigenspace. But that's if you are in this situation. Now the question is how exactly we diagonalize A. And the problem is that if you write the matrix of A, it's not a very easy matrix. It might take half a minute to actually write that. So let me take 1/2 outside. So what you will see, what you will have is a matrix which has zeros on the diagonal, once immediately above the diagonal, once immediately below the diagonal, and then you have two more entries in the corners. Where they come from? Well, from here. What you put in position 1 is half of x2 plus xn. So xn is next to x1, so that's how it comes around. So that's a matrix. Now, if I gave this matrix as a problem in linear algebra and ask you diagonalize this matrix, I'm quite sure that greater majority of my class would be unable to do that. Because even just computing the characteristic polynomial of this matrix is a pain. I mean, it's not impossible. You do expansion in the first row. The first row, so you write A minus lambda I, you do expansion in the first row. The first row has 3 non-zero entries, so it will be sum of 3 terms. Not impossible, but certainly unpleasant, I would even say painful. And greater majority of us would be unable to complete it by just brute force. That's because most of us are mathematicians. Physicists would probably be able to complete it by brute force. They're not afraid of things like that. So what do we do? Well, given that the title of this lecture, you might guess that the answer is in the following. This problem has a symmetry. What exactly I mean by a symmetry? Well, you might observe that the problem will be unchanged if I rotate the table. So there is a clear rotational symmetry in this problem. How we can put it in more precisely, what exactly it means to say the problem does not change. Clearly, the numbers will change. So x1 will go to x2, x2 will go to x3. So it's not like that all the configuration in our system, all the possible states are symmetric under rotation. That's not what I mean by saying that the problem has symmetry. So what's a good way to explain, what's a good way to explain in what exactly it means that this problem has this rotational symmetry? What's the best mathematical expression for that? So we can actually, so if you take R, if you denote by R the operator which sends x1 through xn into, say, x2 in other words, the operator which cyclically rotates all the n entries. If you look at this operator, then the one way of expressing what it means to say that the problem has rotational symmetry is that if I rotate this rotate my configuration, then do the operation A, this stealing serial operation, and then rotate back, it's the same thing as if I did not rotate at all. So if before doing my operation I rotated and then rotated back, that's the same as doing my original operation. In other words, it means that your operator A has the property that A, if you conjugate it by R, is still A. So that's the mathematical way of expressing that my problem has a symmetry. Okay, so we now know that it has a symmetry. We can explain what it means. How does it help us? Anyone has any ideas? I know you were in the class where I was discussing that, so you cannot answer that. So anyone else knows or can guess how we can make use of this fact? No one? Here is, okay. If you guys know the answer and are just shy to say it, well, don't be. That's
Wait, I have
really,
a small question,
yep.
Professor.
Sure.
What is xn like? Does it matter what xn is? Is it like a number?
All of them are numbers. All these x1 through xn are numbers representing the amount of serial in each
Oh,
block.
sorry. Is it like a no? Is there a limit to what xn is? Is like xn like it becomes a different problem if xn is a different number, different index.
Sorry,
Or
I'm
wait, is
not
this an
sure.
infinite amount of seriables?
Just a second now. N, so there is lowercase n, which is the number of kids sitting around the table.
It doesn't matter what the number of kids sitting around the table is. Sorry, I can't ask questions.
Well, at the moment, let's suppose that it's fixed. Let's suppose that there are exactly 17 kids sitting around the table. So it's an interesting question whether the solution we can suggest works for any number or it is something specific. If it makes it any easier, let's pretend that n is equal to 17. So there are exactly 17 kids sitting around the table. And yeah. But that still doesn't help us very much because computing determinant of 17 by 17 matrix by brute force is certainly not a pleasant experience. So how exactly can we make use of this symmetry observation? Sorry, this one. Okay, so here is a lemma, which is trivial. The proof of that I'll give in a minute, but it is crucial for understanding what follows. Suppose that you have two operators which commute, and assume, moreover, suppose that that one of these operators, the second one, is diagonalizable. Moreover, assume that lambda i's, that all eigenvalues are distinct. Then these VI's, the eigenvectors for R, they are also with different, so then the claim is that if you can do that, if you can diagonalize operator R with distinct eigenvalues, then any operator which commutes with it is also automatically diagonalized in the same basis. Of course, the eigenvalues will be different. So that's the lemma. Once I stated this lemma, so in particular, essentially it says that in such a situation, A and R can be diagonalized simultaneously. So if you have two commuting operators and one of them can be diagonalized with distinct eigenvalues, then you can diagonalize both simultaneously in the same basis. How many of you have seen this statement or variation of that? Can you raise your hand using the button? So I know if this is completely new or you have seen it before. Yeah, okay. No one else had seen it? Okay. But, however, this is trivial to prove. I could leave it as an exercise, but let me do that. The proof is as simple as that. So if you look at the vector AVI and apply R to it, then since they commute, you can interchange them. So the simple statement is that in this situation, if you'll start with eigenvector for R VI and apply to it A, one line computation shows that then AVI is also an eigenvector. So it's in the same eigenspace. Eigenvector with the same eigenvalue, same lambda I. But if R is diagonalizable and eigenvalues are distinct, it means that for every eigenvalue lambda, there is exactly one-dimensional space of eigenvectors with this eigenvalue. So if VI is an eigenvector with eigenvalue lambda I and AVI is also eigenvector for R with the same eigenvalue, then it means it must be in the same space. That's the proof. So it's basically the statement that eigenspace for each eigenvalue, the corresponding eigenspace for R is one-dimensional, and A must preserve this eigenspace. Therefore, of course, it must act on it by a constant. So the proof, as you can see, is quite trivial. Okay. So the question is, why did I give you this lemma? Does it help? Well, it does. So here is the situation. We have two operators. One operator A is the one we wanted to diagonalize in the very beginning, and that's a rather complicated one. But then we found another one which acts as a symmetry, which is to say it commutes with A. And now we have the lemma which says that if we could diagonalize R, and if we were lucky that the eigenvalues are distinct, then we would immediately get diagonalization for A for free. So can we diagonalize this operator? The operator of cyclic permutation of entries. Any suggestions? Can we diagonalize the operator of cyclic permutation of n entries? And first statement is that you don't need to write characteristic polynomial to answer that. I mean, you can, of course, if you really want to, but you can diagonalize this operator quite easily without any polynomials whatsoever. And you can find eigenvalues and you can find eigenvectors. Mm. And here is the answer. Yes, you can easily diagonalize your operator R, namely, if you look at a vector which looks like this, just powers. So if you take a root of unity, nth, nth root of unity, so there are many roots of unity of given degree. So for any n, there is exactly n roots of unity in C. Let's choose one of them. So whenever we have a root of unity, you can write this vector, which is just powers of this root of unity. And it's immediate that as you cyclically rotate the entries, your vector is multiplied just by the same epsilon I. The only place where it's not immediately obvious is at the end. So the first, and you need to pay special attention to the first and last entry, because that's where your cyclic permutation is really going over from last to first entry. But it's still pretty easy exercise. It becomes even easier if instead of writing the entries in a column, as we normally do, you write the entries again around circle, around table. So diagonalizing R is trivial. And notice that in fact, that all eigenvalues are different, namely all eigenvalues are exactly n roots of unity. We know that there are exactly n of them, they are all distinct. So each eigenvalue has multiplicity 1. So we are exactly in a situation when we can apply this lemma. So we have two operators, one which we want to diagonalize but could not yet, the other which is much simpler and it acts as its symmetries. And if we could diagonalize the second one, the symmetry one, then the first one would be diagonalized automatically. And we have diagonalized the symmetry, the R. Here are the eigenvectors. Now it's a trivial exercise to check that in fact the lemma does hold, namely if you look at each of these vectors, then each of them, not only it's an eigenvector for R, but it is also an eigenvalue, an eigenvector for our original operator A, for the operator of averaging with neighbors. And therefore, we can diagonalize A and answer the question I asked in the very beginning. Okay, that took me longer than expected as usual, but okay. I'll leave it to you to find the final answer. Is it true or not that after you do it sufficiently many times, all eigenvalue, all amounts will equalize? So in the limit, you would have the powers of your A being projectors on the one-dimensional space with all entries being equal. So for n equals 3, for example, it's true. For n equals 2, well, the problem makes sense, but for n equal 2, it's obviously not true. So you can figure out when exactly it is true and when it is not. Notice, however, one interesting thing is that in order to solve this problem and to diagonalize your operator A, all that we needed to go to complex numbers, roots of unity in C. So there is the only way to properly answer the question about fair distribution of serial is introducing complex amounts of serial, which of course not really surprising to any mathematician. Okay, so that's the answer to the original problem. Of course, it's a baby problem. As I said, given enough determination, we could have solved it without any special observation. But it's, so let me tell you some problem which is less of a baby problem. Still a baby problem, but less of that. So, same thing, only your vector space, which before was Rn, because we had n numbers in a circle, now let's consider the vector space, which are functions on a circle. On the whole circle, continuous, not endpoints. And let me stop pretending and say explicitly that I'm talking about complex valued functions. My operator A from V to V, so I think of S1 as being R mod, say, 2 pi Z. So I think of S1 as real numbers modulo 2 pi Z. So you think of an angle parameterized by an angle. And your operator A is, well, I don't know, something as simple as just A equals second derivative, where X is coordinate on R. Can we diagonalize that operator? This problem I expect many of you, most of you actually have seen. Probably in slightly different language. So it's a question of diagonalizing the operator of second derivative in the space of functions on the circle. And of course, I expect that all of you know the answer. You might not realize you know it, but when I tell you the answer, you'll certainly recognize that you had known it all along. But if, let's pretend all together for a second that you don't know the answer yet. Again, that's a baby example, but can we try and approach this problem in a similar way? Are there any symmetries of this? And we already know what the word symmetry means. It should be something, some operator on this space of function which commutes with A. So that applying this operator and then applying A, it's conjugating A by that operator doesn't change the problem. Is there any operator which commutes with A? Anyone knows of such an operator? And it's probably easier if indeed of mental picture of a circle, you would have a picture of R mod Z, 2 pi Z, so real numbers identified by shift, by integer multiple of 2 pi. So is there any operator which commutes with the second derivative or with the first derivative? So if anyone can guess something, can you write it in chat or say? So is there any operator which commutes with derivatives? Let's even forget for a second that we are on S1. If I were on R, on real line, are there any operators which commute with the derivative? Operator on the space of functions.
Scaling?
Yeah.
Scaling, yes, sure. You can multiply every function by a constant, but that's not really very useful. Of course, scalar operator commute with anything at all, so it's not really specific to A. It's not so much symmetry of A as it is just a statement that A is a linear operator. So we do want something which really explores the feature, is more specific to A. So are there any operators which commute with derivatives on R? Non-trivial operators on the space of functions.
Can we translate the function?
Yep. So as you probably know from pre-calculus, moving the graph of the function t units to the right is equivalent to shifting the argument by minus t. Okay, but now certainly it is easy to see, for example, using chain rule, if you must, that of course this commutes with derivatives and therefore with second derivative. What is less trivial is so again, it's the same thing. It's translation along R, or into, if you like, rotation of the circle by angle t. We now have a minor problem. Before we had one operator R. Now we have a lot of them. One operator for every t. Which of them do we use? We now have abundance of symmetries, maybe too many of them. So which of the operators t do we want to use? Can we use one of these operators? Again, we are thinking of the same lemma here. Of course, the word diagonalizable and basis might need some minor adjustment because after all, it's infinite dimensional problem. And of course, proper understanding what I mean by basis becomes less trivial, but let's completely ignore that for the moment. Let's pretend the space of functions on R is finite dimensional. So can we diagonalize this operator? One of them, or all of them, or some of them, for different t's. And it turns out that in this case, we can. And in fact, first of all, we are lucky because we do have a lot of symmetries, all these rotations of the circle by different angles, but they all commute with each other. And the same lemma as before basically says that if you have operators commuting with each other and you can diagonalize one of them so that the eigenvalues will be distinct, then all of them will be diagonalized for free. So if you have a bunch of commuting operators, then you could hope that you would be able to diagonalize all of them at the same time. And indeed, that's what happens here. See, I. No, I won't use I. So I claim that there is a basis which is a common eigenbasis for all of these translation operators. The eigenvalue will depend on t, on how much you're translating or by, and it will also depend on the index k, but all of them will be eigenvalues. These functions of k will be common eigenvectors for all of the translation operators. How many of you know what this basis is? come on, that's really, you do know that, you just don't know that you know it. Here is the answer. I'm sure you have seen this before. So it's obvious that if you shift x, replace x by x minus t, each of these functions will be multiplied by a constant, namely e to 2 pi I k t. So these, of course, are the complex exponents. And k is an integer, so it's not a non-negative integer, it is an integer. Negative values allowed. So this is a basis. Well, in what sense it is basis? Well, that's the whole question of Fourier analysis. Is it true that any periodic function can be written as linear combination of complex exponents? And the correct answer, of course, depends on what you mean every function and what you mean linear combination. Of course, if you insist on finite linear combination, then that's not true. But if you consider converging, instead of finite linear combination, you consider infinite sums, that is to say series, then yes, for good functions, for example, for C infinity, it is true that you can write any such function as an infinite sum of complex exponents. That's the main result of Fourier theory. Well, one of the basic results. So it's not the main, it's the basic. But let's not go there at the moment. I'm not interested in analytic questions at all. What I'm interested in is observing that these functions are common eigen basis for all of our translation function, or rotation. And therefore, according to the same lemma, you could expect, if you could also compute the eigenvalues and check that they are all distinct, you could expect that therefore any operator which commutes with the translations, in particular this operator of second derivative, would also be diagonalized in this basis. And then of course it is true. It's trivial to check that complex exponents are diagonalized. Complex exponents are eigenbases for derivatives. I'll leave it to you to find the constant. So we have diagonalized the operator of second derivative and also of the first derivative. And in fact, the same basis diagonalizes any operator which commutes with translations. So that's really the meaning of why these complex exponents appear so frequently in Fourier everywhere, and why the whole subject of Fourier analysis appeared. It's not just, it is some kind of basis in the space of function. This basis has a very special property. It plays nicely with the action of rotations or translations along the real axis, whatever language you prefer. Namely, this is an eigenbasis for all of these translations. That's the reason why this is so useful. Okay, but that was still a baby example. Let's do a less baby example, the real example. And this example has a name, and the name is this. It's all very similar to the previous problem, but vector space will be a space of functions, well, let's say complex functions on S2, on a sphere. And my operator A is the so-called spherical Laplace operator, which I'll define in a second. It is basically, you know, there is the usual standard Laplace operator, which is del 2 over del x squared plus del 2 over del y squared plus so that's the usual Laplace operator, which I expect most of you have seen. It's effectively what we want is to restrict it to the sphere. It doesn't make literal sense because, for example, if you have a function which is only defined in the sphere, you cannot take the second derivative of that with respect to x, partial derivative. To know partial derivative with respect to x, you need to go outside the sphere. However, it is, you can make it, you can restrict it to a sphere with a little bit of work. So namely, you can check that if you, that this usual Laplace operator, you can rewrite if you make change of variables going from x, y, z to r. So if you do the spherical coordinates, yeah. Then this Laplace operator is written in some special form. I don't really care very much what it is, but unless I'm mistaken, that's the correct answer. And this operator, which we have here, it is differential operator on the sphere, which is to say that you can apply it to a function which is only defined on the sphere, and in order to compute it, you only need to know the values of the function on the sphere. You don't need to go away from the sphere. You can write it very explicitly in terms of these angles phi and theta, which is the usual spherical coordinates, but believe me, you wouldn't enjoy what you get. It will be a very ugly expression, much worse than what I had written. What is important is that you do have some kind of differential operator of second order, including second derivative, which is defined on the sphere, which is defined for any, so you can compute it for any function defined on the sphere. And you can ask the same question. So can you diagonalize this operator in the space of all smooth functions on the sphere? It's very much like what we had right here, except that it's harder. And however, this has a really meaningful physical, it has a real physical meaning. It's not really any longer a toy model. It's a real model, namely, that's part, and in fact, that's the most important part of what is needed if you are trying to describe quantum mechanically an atom, a usual atom. So, but let's, in some simplification, assuming that the nucleus is just a point, and so you have an electron around this nucleus. So you are trying to find, so quantum mechanically, you know how to describe it. So you have this Hamiltonian, the energy operator, you need to find the energy levels, you need to diagonalize that. And after a little bit of technical work, which I'm certainly not going to describe, the really meaningful part of that is diagonalize this spherical Laplace operator. If you can do that, then you can find the spectrum of the hydrogen atom, or in fact of any kind of atom in this simplification. And that's certainly very useful physical information, because, for example, when you look, for example, so if you look at whenever you're doing any kind of spectral analysis of any star, the first thing you want to see, the first thing you see are exactly these jumps which correspond to electrons moving from one energy level to another. So can we do this problem? Of course, if you are a physicist and you are brave and you don't care about any of these mathematical fine points, you just write this in coordinates and you solve the corresponding differential equation in coordinates. I don't want to do that. So what's the better way? Well, by now you can probably guess how you would do that. The nice part about this is that it's not some random operator. This operator has symmetries. Laplace operator is symmetric with respect to rotation of R3. Again, the word symmetric for an operator means the same thing as before, namely that it commutes with any rotation of the three-dimensional space. If you look at this, how I define the spherical Laplace operator, the operator on the sphere, then it's immediate that it also is invariant under rotations. So this operator, whatever it is, has a huge number of symmetries, namely all rotations of the sphere. So the natural question, what we do with it, would be a natural approach to what we do with it would be, well, let's do the same thing as before, namely let's go back to this lemma and use that. There is, however, a problem. There is more than one rotation, which we also had in the previous example when we were talking about rotation of the circle. However, when we were talking about rotation of the circle, we were lucky in that all rotations of the circle, or if you like, all translations on the real axis, commute with each other. Yep. And yeah, and Eigen, you are exactly right, of course. So the problem we have in 3 dimensions, or rather on the 2-dimensional sphere, is that rotations of the 2-dimensional sphere don't commute. And therefore, we might be able to diagonalize one of them, but it's certainly impossible to find a base which diagonalizes all of them, because they don't commute. And of course, if they were diagonalized in the same basis, then they would be commuting with each other. So that certainly is not going to happen. And if you do a little bit more analysis, you'll see that diagonalizing one of them is not good enough. So any one of them you diagonalize is not going to have distinct eigenvalues. So this naive idea of just taking symmetries, one of them or all of them, and diagonalizing them does not work, because in the case when your group is not a commutative group of symmetries, you cannot diagonalize them at the same time. So what do you do? Well, the proper answer is that you actually, and that's what representation theory does. So let me. So the problem is that rotations don't commute. So we cannot diagonalize them all at the same time. So we need something else. And since I have exactly 1 minute left, clearly I cannot properly describe to you what is the right answer to that. But the appropriate solution is that so before what we were basically writing, we was saying that you take a vector space and you write it as direct sum of 1-dimensional spaces. Each of them was eigenspace for R. So that's what we had before. That doesn't work anymore. what works instead is that you take the same V, the same vector space, and you write it again as direct sum of some subspaces V. But now they are not necessarily so what you basically do is you replace one-dimensional space, which was just the eigenspace, which is what we used before. You replace it by the best you can, namely you try to break your vector space as direct sum of vector subspaces, each of which is invariant under the action of your group SO3, in other words, invariant under rotations. And you try to make this, break it into as small pieces as possible. As I said, there is no hope that these pieces will be one-dimensional, so these pieces will be what they are, and they are called irreducible representations. And then with this change, the same algorithm as before goes through. So if you can decompose the space of functions on the sphere into simple representations of the group SO3, then there is a general argument which says that in this case we can get the same result as before. As soon as you have done that, you automatically have diagonalized any operator which commutes with all rotations, in particular our spherical Laplace operator. And therefore now the question is no longer about solving partial differential equations, but it is a question of studying the action of the group, in this case the group of rotations S of 3, in some vector space, in this case space of functions on the sphere. So if we know how to analyze this action and decompose your vector space into smallest possible pieces, then we have solved our original problem. And that can be done. So if I had another hour, I would actually complete the story, but I don't have another hour. And if you do that, in particular, that explains why if you actually do complete the story and you diagonalize the spherical Laplace operator, you find that its eigenvalues have multiplicities. That's exactly because the multiplicity comes from these smallest pieces appearing here, these pieces. So for example, it is known that for this particular situation, you have a whole sequence of eigenspaces indexed by non-negative integers, and kth eigenspace, sorry, not eigenspace representation, kth representation has dimension 2k plus 1. And that's exactly the multiplicities you see when you do finish the problem of diagonalizing the spherical Laplace operator. So that's an extremely powerful tool, which certainly is by far the easiest way I know of solving this problem. And this solution agrees perfectly with experiments. So indeed, all these energy levels you get by diagonalizing the diagonalizing the Laplace operator, they all exactly match to what is observed experimentally, in particular in spectral analysis of stars, or in fact of any heated gas. And that was one of the greatest triumphs of quantum mechanics, of early years of quantum mechanics. And as I said, what makes it possible to do without tearing your hair is using symmetries. So whenever your problem has symmetries, it's much easier to solve. That's the one-line summary. Okay, I'm afraid as usual, I didn't have time to cover all the things I wanted, but then I should have expected that. So let me stop now to maybe leave some time for questions. Okay.